Great. So, right. So indeed, so the title, Hitchin systems in supersymmetric field theory. Okay, so let's fix a compact Lie group G. But okay, much like in David's talk this morning, I'm going to be a little bit sloppy about the various different forms of the same compact forms of the same Lie algebra. So I'm not going to really distinguish between SL2, PSL2, that kind of thing. One could do better, but at this first go around, I won't try. Let's also fix a compact Riemann surface C. From these data, as presumably many of you know, there exists a space, kind of famous space, which I'll write mg of C, which is Hitchin's integrable system. So among its well-known properties are, first of all, that it is indeed a complex integrable system. So it comes to you as a torus vibration over some base, where the dimension here is the same as the dimension of the fibers. It's a holomorphic symplectic manifold. In fact, it's a holomorphic symplectic manifold in many different ways. In fact, it's a hyperkähler manifold. So all those holomorphic symplectic structures kind of fit together. It's hyperkähler, so it has a family of holomorphic symplectic structures. Labeled by a parameter, say zeta, lying in CP1. So sometimes people define hyperkähler to mean that it has 3 complex structures and 3 corresponding whole symplectic structures. As soon as you have those 3, you actually have a whole CP1 worth of them. So think of it that way. So I want to, so suppose that we're interested in studying this space. I'm going to tell you some new structures that this space has. And the way that we're going to get these structures is to embed Hitchin's integrable system into somehow something much, much bigger. So the main point today is that this space, mg of C, mg of C is part of something much bigger. Is part of a certain supersymmetric quantum field theory. And I guess I can give even the name of that supersymmetric quantum field theory with respect to this chart that we have here. So let's see. So I start with theory X, and it's going to be one of the things that I get by compactifying theory X. Oh shoot! But you called your Riemann surface sigma. So it's going to be this one. So it's going to be X on sigma cross S1. So the name. So I'll write it like this. So theory X is the 6-dimensional thing. I call it X sub G to keep track of this Lie algebra. And then we're going to compactify it on C cross S1. So that's where we're headed. So I want to explain that. And OK, so I guess there are 2 points. So the main points, that's the first point. The second point is that you can use this to see new things about mg of C. And I'll describe one example either today or in the next lecture. And this is kind of the most decategorified thing that you could imagine. So embedding it into quantum field theory is something pretty fancy, but I want to extract something that I can actually understand. And one thing that you get concretely is some distinguished local coordinate functions. Or local coordinate systems, I should say. Distinguished local coordinate systems, which I'll write x gamma of zeta. And so the statement is that when I say distinguished, I really mean distinguished. I mean around every point of this, every generic point of the Hitchin space, there's going to be a totally canonical coordinate system. And using these totally canonical coordinate systems, you can do a lot of things. For example, you can, they're sort of the beginning of a scheme for actually. Sorry,
can you say again what is gamma, what is x, and what is c?
Yeah. So as I said, there's going to be these local coordinate systems. So what are they going to be labeled by? So more detail. So the Hitchin system is fibered over some base. So let me draw that base for you. The physics of this base will become clear as we go along, but for now, let's have a mathematical thing. So this base carries over it a local system of lattices, which you can think of as just the homology of the tori.
Right, and it's useful
yeah.
if you can keep things above a certain.
Oh, sorry. Keep it above, and this is below.
Yeah, that probably is a bit below.
Okay. Yeah. So what are these x gamma of zetas going to be? So what we're going to have, the Hitchin base B. Inside of there's going to be a discriminant locus. And away from the discriminant locus, let's call it B regular, B minus B discriminant. And we're going to have a local system of lattices. Literally lattices, so free abelian groups. Gamma over the regular part. And then these coordinate functions, so the local coordinate functions around a given point of M will be indexed by vectors gamma in gamma, and the parameter zeta that appears here is the twistor parameter. So I said that there's a CP1 worth of complex structures. So in any one of those complex structures, well, in any one of the in a C star worth of those complex structures, there's going to be a totally canonical coordinate system around any point. That coordinate system is going to be most canonically indexed by elements of this lattice.
That C star is everything which is, so to speak, not the Hitchin.
That's right. So this space has the sort of funny property that almost all of its complex structures look the same, and then there are two that are special. And that's right. So the two that are special are the ones in which it literally looks like a fibration by compact complex tori here. There it would be somehow hopeless to have local coordinate system that cover these tori, because the torus has no holomorphic functions. So we're not doing those complex structures, but you do all the rest.
And can you tell me, are these coordinate charts algebraic in the Duran picture and the Betty picture?
I always forget which is which. Which is the one that's representations of the fundamental group? Betty. They're algebraic in the Betty complex structure. Yeah.
So when you said on number 1 that there was C plus S1,
Yeah.
David made a comment at the beginning of his talk that there was sort of data in an S1, and I was just wondering if it's the same S1 that went from little g to capital G.
It's the same S1, but I'm being just sort of equally as sloppy here about the. To be really honest. To be really honest, the spaces that you encounter in this business, okay, so this is for people who've thought a little bit about the Hitchin system before. So the Hitchin system has this property that it has, there's a sort of T-duality, there's mirror symmetry that relates the Hitchin system for G to the Hitchin system for the Langlands dual of, sorry, I'm supposed to, for the Langlands dual of G. And to be honest, the space which we encounter is lying in a sense halfway between these two. The spaces which we really encounter are actually self-dual under T-duality. So it's not exactly MG or MLG. On the other hand, even at the level of the hyperkähler structure, if you just think of them as Riemannian manifolds, one of these is just a discrete quotient of the other. So at the level that I'm interested in, I'm not going to worry too much about this. Okay. Okay. All right. So the aim is to somehow embed this thing into supersymmetric quantum field theory. So how are we going to do it?
And you were going to say what
Oh yeah. I mean, one use of these coordinates is to actually construct the hyperkähler metric on these spaces. So usually the hyperkähler metric on these spaces is known, but it's known in a very implicit kind of way. So this is a way of getting more explicit construction of it. But that's, from the point of view I'm trying to take, at least in this talk, that's just kind of a certification that this structure is actually useful for something. What I really want to tell you today is what the structure is. So the starting point, of course, is the same as in David's talk, but I'll repeat a little bit. So let's fix now a Lie algebra G of ADE type. So then it's believed by physicists, that there exists a six-dimensional interacting quantum field theory, which I'll call XG. Let me say, even this is already very non-trivial. So for a long time, it was believed that there were no interacting quantum field theories above 4 dimensions. And in the 90s, people figured out how to use string theory to construct this six-dimensional theory. And so now it's believed that there are no interacting quantum field theories above 6 dimensions. So you should imagine that this is some isolated and very sort of beautiful jewel of an object. So if the lower you go in dimension, the easier it is to make quantum field theories. In 2 dimensions, you can make 1,000,000 of them. In 4 dimensions, you can make plenty of them. In 6 dimensions, it seems that there's just this. It's just this thing. Okay, so what are the basic facts? The basic facts about this
Sorry,
thing.
Andy, can you say the word interacting means something like non-abelian?
Well, interacting. Okay, so what the technical meaning of interacting is. Let me say what it would mean for a. Interacting means it's not free. For theories with a Lagrangian, it would be very easy to say what that means. So it means, for example, that that the Lagrangian is not purely quadratic. In other words, the equations of the theory are not purely linear. So linear, one trivial thing which you can have is you can have a theory where all the equations are linear. That's called a free theory. Free theories you can construct in any dimension. But this, I'll just say that it's not a free theory. It's not obtained by that construction. Okay, so what are the basic facts about this theory?
So is the statement then that we don't think there are interacting QFTs above dimension 6? We know there are no Lagrangian interacting theories above that?
You hate to say that you know anything for sure because it so often happens that there's a sort of proto-theorem in physics and then it gets, it turns out that there's some loophole. I think I better say it just the way I said it here. There's none known, but there's no. Okay, so what are the sort of basic things that are believed about this theory? So first of all, it has so-called n equals 2, 0 supersymmetry in 6 dimensions. What does that mean? So just very roughly, what it means is that so to be a 6-dimensional quantum field theory would have meant in particular that it has, you formulate it, your space-time is literally R6 or R5, 1. Let me try to be in Minkowski's signature, so R5, 1. And then everything in the theory is supposed to be invariant under the action of the isometries of R5, 1, the Poincare group. Now to say that so that's one thing this theory is supposed to have. But in addition to that, it's supposed to also have this supersymmetry. And what that means is that there's a certain super extension. So it's a supergrouper, at least a super Lie algebra. So a super extension of the Poincare group, ISO 5, 1, which acts on everything in the theory. So for example, the space of operators of the theory is acted on not only by this ISO 5, 1, you can not only move them around by the Poincare symmetry, but you can also transform them by these additional odd generators. And things like correlation functions are supposed to be invariant under this symmetry. Okay, so that's the first thing. And this 2, 0 just tells you which super extension it is. So there's some particular super extension. Yeah, I shouldn't say actually that this is the only theory in 6 dimensions. So there's also theories in 6 dimensions with n equals 1 comma 0 supersymmetry. That's true. So it's not quite true that this is the only thing you can have, but it is believed this is the only thing you can have with this kind of maximum amount of supersymmetry. Okay, the next thing about this theory is that it has no parameters. It's totally rigid. So unlike many quantum field theories which depend on couplings or scales of things, this theory depends on nothing. Kind of isolated object. Okay, now what does it mean even to have a quantum field theory? So if I could tell you the definition of quantum field theory, I would very happily do it. I can't, but let me say a few things. So the first thing is that this theory. So one of the things you're supposed to have in a quantum field theory is you're supposed to have a notion of the space of operators, local operators. Yeah.
Does that the fact that it has no parameter imply it must be conformal because it must be a fixed point of the representation?
Because it doesn't have any scale. There are some. I think that presumably the fact that it has no parameters presumably implies that the theory is scale invariant. Now there's some sort of ongoing debate in the literature about whether scale invariance implies conformal invariance or not. So I'm not sure whether conformal invariance follows simply from this property. Nevertheless, it is certainly believed. I could have said, I could have added. Yeah. So let's put it here. That is indeed supposed to be conformally invariant. So in fact, I mean, I said this 2 comma 0 supersymmetry, but in fact, there's even a further extension of that to the superconformal algebra. Yeah.
This theory is interacting, but there's no parameter, then how does the interaction strength?
So that's the amazing thing, right? Right. So usually when you have an interacting, so we're used to the idea that when you have an interacting theory, that there's a parameter that controls the strength of the interactions. Not so here. This theory, the strength of the interactions is just fixed. It can't be perturbed. The reason for that is that the theory has no Lagrangian. Otherwise, it would be obviously inconsistent. If you had a Lagrangian, you could always kind of change the parameter in front of the coupling. But this theory, that's one of the next things, is that as far as anyone knows, this theory doesn't have a Lagrangian, and so it's not obviously inconsistent, what I just said. Right. Okay, so let's just say that next, in fact. So this theory is not believed to be given in the so-called sort of conventional way. So by a space of fields with a Lagrangian. Maybe I should say is not believed to be given by path integrals over. Yeah, so sometimes when people try to define quantum field theory, they'll say, well, it's a machine that produces numbers, and the way that it produces the numbers is by doing path integrals. This quantum field theory is a machine which produces numbers, but it does not do it by path integrals. Okay, yeah.
Some other have a space of fields?
No, it's not. It simply doesn't have a space of fields, as far as anyone knows. It just can't be defined in that way. So the only constructions of it. So all known constructions. Yes, you can say how do people know that this theory even exists at all, right? So the bad news is that all of the known constructions use string theory, and so that means you have to accept first the existence of string theory, which is much harder to construct, and then I should say today. So very recently, the situation may be improving, and I think you may hear about that in Kevin's talks, actually. But up till today, it's not really known how to make this thing without using string theory.
Can you just say, so to speak, inputs or what? I mean, out of what does it produce a number?
Okay, I'm coming to that. So right. So let me go just slightly further, and then repeat the question if it's not satisfactory. So it has local operators. So in the usual path integral thing, one of the things you do is you compute path integral and you insert local operators in the path integral, which are functions of the fields at some points. Here we don't have the fields. We don't have functions of the fields. But nevertheless, there's a notion of what the local operators are. So I'll write them. It may have more than this, but these are the ones. These are some ones that we know about. I'll write them phi upper I lower f, labeled by. So what are these labels? So I is just the index that goes from 1 to 5. And f is supposed to be an invariant polynomial in the Lie algebra G.
Is that 5 the same 5 as 6 minus 1?
It is 6 minus 1, but in fact, it's 11 minus 6. Yeah, so what I mean by that, it's a serious thing. One way of understanding where this 5 comes from is that, so let's use one of the ways that this quantum field theory gets constructed. It gets constructed by starting with M theory. M theory is 11-dimensional. And inside those 11 dimensions, you pick up a 6-dimensional subspace. So here's R6 sitting inside R11.
And that's the space-time R6.
That's the space-time R6 of this superconformal field theory. But in the string theory construction, it's sitting inside a larger thing, which is R11. And therefore, one thing that you see right away is that, so this theory evidently has SO6 acting on it. Or I guess I wrote 5, 1 before, so let me try to continue to be careful about that. So 10, 1 and 5, 1. So this theory evidently has SO5, 1 acting on it. At least the way I set it up, it looks like it. But it also has the rotations in the transverse directions. So it has another symmetry group, which is SO5, the other 5 directions. And that SO5 acts on everything in the theory. It's called an R symmetry of the theory. And in particular, it acts on these operators. So these operators come in a multiplet, and the reason why there's 5 is somehow because of this SO5. So it's not the 6 minus 1 if what you thought was, if you were thinking of the internal 6, it's not those.
Okay, great.
So this 1 to 5 is presumably the basis of some vector space?
Yes. Yeah, that's right. That's right. So it would have been more natural to say maybe that.
Is there a basis-independent way of naming that vector space?
Yeah, I mean, it's the transverse space to this. Sure. Yeah, no, I mean, yeah, maybe I shouldn't have written it this way. I should have just said there's the fundamental representation of SO5. And choosing any element of that fundamental representation, you get an operator. That's right. I wrote it this way just to be a little bit quicker. But no, there's no choice of basis here. What you really have is a 5-dimensional vector space which is acted on by SO5. It's the fundamental representation of SO5. I don't know how else to say it. You're not satisfied by this? Okay. So for example, all right, so this is an aside. So for example, just to be really concrete, if this Lie algebra G was AK minus 1, this is kind of the most popular case to think about it, SUK. Then what do we have? We have phi I. So here the invariant polynomials, I can just write them phi I2 up to phi I k, where so I'm just saying that we have one invariant polynomial in each degree, so they're corresponding to invariant polynomials. Invariant polynomials f of x equals trace of x to the n, where n equals 2 up to k. Okay, so one thing we think we know about this theory is what its local operators are. I'll say in a minute what local operator means if you haven't seen it before. But let me go on just a little more first. So the theory is also supposed to have surface operators. And those are labeled by irreducible representations of G. Plus, so here let me say it in the more basis independent way. So plus a vector in R5, the same R5 that was over there. And it's also supposed to have 4-dimensional operators, in other words, codimension 2, 4-dimensional operators. And those are labeled by roughly, nilpotent orbits in GC. And plus. So again, there's this little choice. In this case, it's a 2-plane in R5. OK, so what does it mean? So I said all I've told you about this theory really is what its symmetries are. Plus, I told you it has local operators, surface operators, and 4-dimensional operators. So roughly what does that mean? What you should think it means is that so xg is supposed to assign a number to something. And what is that something? That something will be a 6-manifold, a Riemannian 6-manifold. Sorry, Lorentzian. Well, yeah, Lorentzian 6-manifold. Actually, for this it would be better to do the Euclidean version. So let me talk about so these theories, in general, you believe that you can sort of continue them back and forth between Euclidean signature and Lorentzian signature. So just for this statement, let me say it in Lorentzian signature. So xg, the Euclidean version, is supposed to assign a number to a Riemannian 6-manifold, a compact Riemannian 6-manifold. But then to say that the theory has these operators is to say that you can also insert in that 6-manifold various additional stuff. So here's my 6-manifold. And then inside of it, I can put points. And those points, each point is going to be labeled by a local operator. So I told you the local operators that we know about. So we're allowed to put local operators on points. And then we're also allowed to have surface operators, which are inserted on 2 manifolds. And then we're supposed to have we can insert these 4-dimensional things. These 4-dimensional things, which are called 4-dimensional operators. So what this quantum field theory is supposed to do, at least one thing it's supposed to do, is it's supposed to be a kind of machine that produces a number out of this data.
In this data, am I allowed, are there any rules about how the points and surfaces and boy things have to touch each other or not? Or?
No, these, OK, well, there's of course a question of whether this situation does or does not preserve supersymmetry. Now, for the thing to be sort of most computable, you would like to do it in a situation that preserves supersymmetry, and then there will be all kinds of constraints. The 6-manifold can't be arbitrary. Maybe the points have to be all inserted along a single line. In Kevin's talks, I think you'll hear about a situation where all the points are taken to lie on a 2-plane. That's a nice supersymmetric situation. But sort of abstractly speaking, if I just want to say what is a to give you some feeling for what is the quantum field theory, as opposed to a topological quantum field theory, here I think I'm probably allowed to do anything. Yeah.
So I think I know how to say this in terms of covariance, just to verify. I think when you say local operator, you mean something like cut out a very small ball from the manifold, and then it becomes a covariance from like S5, and then I want to local operator should be something like the vector, something living in the vector space I assigned to S5. Is that right?
As far as I know, that's the expert will confirm, but that's my understanding of things. Yeah, but I should emphasize that this is not a topological field theory. So I think according to Hoyle, according to Lurie or whoever, it doesn't quite fall into that framework. OK, so where did they come from? Yeah, they came from M-theory brains. If you really pressure me, I'll try to remember. I always forget. I think it's M2 brains ending on this. You have M2 and M5. So this thing is the world volume of an M5. So where does the local operator come from? Oh, how embarrassing.
Maybe the discussion of the construction of theory acts can go into discussion.
Yeah. Yeah, I should remember that instantly, but I don't. OK, so it assigns a number to a Riemannian manifold, and it should also assign, for example, a vector space to a 5-manifold, possibly a category to a 4-manifold, and so on. OK. And in all of those, you're allowed to put these decorations. I mean, you can have a 4-manifold. You could have a 5-manifold which is intersecting one of these surface operators, for example, intersecting it in a line, and then that would change the Hilbert space. So it's a relatively rich, once you start including all of these possible defects, it's a relatively rich structure. OK.
Andy, can you not just think of the local operators as the modes of the brains moving in the transverse?
Yeah, that's what it is, right. Yeah, thank you. It's just the invariant polynomials in those scalars. Yeah, that's right. In M theory, that's exactly what you would say. Yeah, right. So sorry. So yeah. So the brain. One of the things about the brain is it's a dynamical object, right? So it has the possibility of just fluctuating in the other direction. I think that's what those local operators like. You measure the fluctuation at a given point. That's what that operator is. Right. Right. And those are not. Yeah. Okay. So what I just told you is some rather short list of information. In particular, I didn't tell you how to actually calculate this thing in any example. And basically, we know very, very little about how to actually calculate these things. So most of what we know about this theory is not about the sort of pure object in 6 dimensions, but rather it's about the compactifications of it to lower dimensions. So OK, as David also said this morning. So what is compactification? Loosely speaking, what does it mean? It means, and this is a thing you could do for any quantum field theory, so call the quantum field theory T in d dimensions. So instead of taking the space-time to be R, d minus 1, 1, let's instead take it to be, simplest thing would be to just take literally a Riemannian product. So y cross, and that'll be enough for everything I want to say, I think, r to the d minus k minus 1, 1. So y is some Riemannian k manifold. Now, I should say, there isn't like an automatic way of doing this. So what I really mean, you're trying to make another quantum field theory whose local physics will be somehow the same as the physics of this one, but where globally the topology will be different. And that may involve some choices. So it's not like people often talk about this as if it's like a totally standard thing. That there's somehow only one way to do it. Oh, just make the space-time different. It's not quite honest. I mean, for example, when I write the Lagrangian for the, imagine that the theory had a Lagrangian, right? When you write the Lagrangian, try to write the Lagrangian for this other theory, you're free to add terms that depend on the curvature of this space. Here, there was no curvature, so those terms would have been 0. So when I put it on here, do I put those terms or not? Well, OK, so there's some choice. And so generally, it's not totally automatic. But nevertheless, people do it. People make those choices. And so it produces, so what do we get? So we get a theory T of y now, which if you kind of view it abstractly, it has less symmetry than the original one, because the original one had the Poincare group acting here. Now this one has only the Poincare group acting here.
The way you said it made it sound like the space of choices is all possible quantum field theories on y itself.
No, because there's some notion, which is a little delicate to say exactly. There's some notion of the local physics being the same. So what you would like to say is that if you look locally, if you look at a tiny patch of y, the local physics should be very similar to the local physics on a tiny patch of r to the d minus 1, 1. For example, the local operators should be the same. The operator products of those local operators should be the same in some sense. So no, it's not like totally unconstrained. OK, so we're going to get a theory now with this lower symmetry. So it has less symmetry. It has less of this bosonic symmetry than the other one, and correspondingly, it usually will also have less supersymmetry. And maybe, so if the original theory had some supersymmetry, and if you were kind of artful in how you chose your compactification, the remaining thing might have some supersymmetry as well. OK. So in particular, so we want to do this for theory X, right? So now again, I'll repeat something that David said. So So for example, so one thing that's pretty simple to do is to compactify a theory on a circle. Because morally, that just means modding out by a translation in some direction. You know, the theory was Poincare invariant, so translations were symmetries. So it should be always possible to put the theory on a circle. And indeed, so it's possible to compactify this theory xg on a circle. And let's give this circle some length. So it's supposed to be a Riemannian circle, right? So let's say a circle of length r. And now you say, well, what do we get when we do that? So okay, you just get another quantum field theory, which is as complicated as the original one. After all, it has all the same local physics as the original one, if you just look close in, you know. So this theory can't be simpler than the previous one. On the other hand, now you can do the following thing. So this next sentence, yeah, I'm going to put this sentence in quotes. So if we consider this theory, okay, so we got here some theory which I'll call T of S1 in keeping with my notation. So T of S1, and suppose we consider T of S1 at energy scales which are much less than 1 over r. So I'm going to amplify a little bit what this means. But the statement is that if you do that, then the physics becomes that of 5-dimensional supersymmetric Yang-Mills theory. With gauge group, okay, now I have the same problem that David had, so I'll say with gauge group G. And coupling, so this theory does have a coupling. The 6-dimensional theory didn't have any coupling, but 5-dimensional Yang-Mills certainly has a coupling. And the coupling will be proportional to R. Okay, end quote. Okay. Okay, so what does this mean? So first of all, what is 5-dimensional supersymmetric Yang-Mills? So I'll first tell you what is 5-dimensional super Yang-Mills, and then I'll try to say in what sense is the 6D theory supposed to look like 5-dimensional super Yang-Mills at long distances. So 5D super Yang-Mills. Fields, okay, so what are the fields, first of all? So this unlike the 6-dimensional theory, this is a theory which, honest to God, has a Lagrangian. So to describe that theory, it's not a bad thing to try to just tell you the Lagrangian.
Why do people miss this theory when they thought everything stopped with dimension 4?
Because, yeah, now this is a very interesting thing. So the statement here is that if you consider this theory at energy scales less than this, then the physics is that of 5-dimensional super Yang-Mills. So 5-dimensional super Yang-Mills is one of these tricky theories which it makes perfectly good sense if you study it only below a certain energy scale. And here we're absolutely studying it below a particular energy scale. But what doesn't make sense, or at least what doesn't obviously make sense, is to consider 5-dimensional super Yang-Mills at arbitrarily high energies. So many quantum field theories exist in this kind of effective sense, where it makes sense at some low energies, but when you try to run up the energy, the thing blows up and something bad happens. People actually now argue about whether 5-dimensional super Yang-Mills is or is not like that. So it could be, naively speaking, 5-dimensional super Yang-Mills make sense at low energies, does not make sense at high energies. No problem for this statement, but it's a problem for saying that it exists as a fundamental quantum field theory. Lately, there has been a movement to sort of upgrade the status of this theory, and some people now claim that it actually does make sense even at higher energies, but it does so in a very, very subtle way. Okay, so yeah, effective field theories are easy to make. Field theories that only exist below some energy scale are relatively easier to come by. I could easily do that in any dimension. I mean, I could write down whatever Lagrangian I want in 100 dimensions. It would only have a problem at high energy. Okay, so 5-dimensional super Yang-Mills, what are the fields? So a G bundle, P, with connection. Sections phi I of add P So here's again this funny 5, I going from 1 to 5. And then fermions. I'll say nothing about the fermions. So these are some kind of fields that have odd statistics instead of even. And what is the Lagrangian? Here's the Lagrangian. Its trace of, OK, we have a G bundle with connections, so let F be the curvature of that connection. Let's call the connection D. FD wedge star FD plus R squared, sum I equals 1 to 5, d phi I wedge star d phi I plus fermions. OK, there's the Lagrangian. So, OK, one reason I'm writing this Lagrangian is to emphasize something. So this Lagrangian, this is not a free theory. This is an interacting theory. Why is it an interacting theory? So to say it's interacting is just to say that the equations that you get from extremizing it are not linear. That's the same as to say that this is not quadratic in the fields. Why is it not quadratic in the fields? It looks quadratic in the fields. The reason it's not quadratic in the fields is that these things are hiding. So FD, for example, is dA plus A wedge A. And the field in this thing is A, the connection. And so this is an interacting theory. For example, this thing has a quartic term in it. So this is not a free theory. It's interacting theory. It would have been free if the group was abelian. We'll come back to that. Later we're going to encounter a similar thing with an abelian group. So I just want to point out that had the theory been abelian, this would have been a free theory. So if G is not abelian.
You have some matter though.
The matter is in the adjoint. So that'll also be if G is abelian, that'll also be free.
Can you translate both those statements? What does it mean you have some matter? What does it mean matter?
The statement that you have some matter is the statement that in addition to a principal bundle, there are some sections of that bundle. And the statement that they're in the adjoint is the section that here you see the adjoint. So in particular, the covariant derivative will just be the ordinary derivative if it happens that the group is abelian. Then add P is just the trivial bundle. OK, great. OK, so I'm still trying to explain the meaning of this statement, that when you compactify the theory on a circle, you get this. So what does it mean? So first of all, the observables. Okay, I want to keep this. I guess I have to erase it. Sorry about that. So the observables of this theory X on a circle can be mapped to observables of 5-dimensional super Yang-Mills. So, for example, so in theory X, we had these things phi I f, these local observables, depending on an invariant polynomial, which I could put. So there are local observables, so they sit at some definite point. So call that point x and x6. So here, x is a vector in the uncompactified R 4, 1, and x6 now is the direction on the circle. So the picture is that we have, we're putting the theory on a circle. So here's the uncompactified directions R 4, 1. Here's this little circle. So we had local operators. We had local operators which we could have inserted at some points in the original 6-dimensional theory. And now, in 5-dimensional super Yang-Mills, there's a corresponding thing, which would be to just take. So in 5-dimensional super Yang-Mills, we have an actual field. We have an actual field, and we could just take the invariant polynomial of that field. So it's an adjoint valued field, but if we take the invariant polynomial applied to it, that's a good gauge invariant thing. Yeah, I should have said here that, of course, we consider this kind of modulo gauge transformations. So the only good observables are the observables that are gauge invariant. So corresponding to this, there's a corresponding 5-dimensional picture where now I've lost this circle. I don't have the x6 direction anymore. But now I can insert the corresponding operators at the same places on the x line in the x direction. So
How many different roles is the symbol F playing?
only one. Oh, sorry, two. Yeah, it's the curvature. Sorry, there's the curvature of the connection, and there's also f, which is the invariant polynomial. But this f is the same as this f.
Okay, and what's the other one?
Sorry, this f shouldn't. Sorry. I apologize. The curvature is f sub d. Yeah, phi I. The fields were just called phi I. Yeah. So and similarly, we had the surface defects. The surface defects. So let's imagine now having a surface defect in this six-dimensional theory. So we could take the surface defect to be wrapped around. So that's the thing that goes on a two manifold. So we could consider it to be wrapped along the circle, and then also have it extended in some other direction. So this is some line in R5, 1, in R4, 1. And corresponding to that, so here now we've lost that circle direction, and so we'll have a line here. So I need some operator which can be inserted on a line. And indeed, in 5-dimensional super Yang-Mills, there's a natural candidate. So let's just say, schematically, the surface defect in representation R. So we had surface defects labeled by representations of the group. And those are going to correspond, after I wrap them around this circle. In 5-dimensional Yang-Mills, there's a corresponding thing which is the Wilson line operator. More exactly, it's a supersymmetric Wilson line operator. So it's written of the form. So this, again, this is something you can really write just as a function of the fields. So if we have this line, L here and here. Well, at least if L was a loop, suppose we close this thing up so it becomes a loop. Then the Wilson line operator is just the trace of the holonomy along that line of the connection shifted by some multiple of the scalars. So remember, the surface defect depended also on a vector, depended on a direction in R5, and that tells you which scalars to put here. Yeah?
So most surfaces upstairs in 6-dimensional space are not going to push forward to...
Yeah, so I'm just telling you about the very simplest thing. So that's right. So the generic thing would be to have a surface here that would give rise to a surface here. And then there's some other corresponding operator, which is called a Tuft operator. But I can't do it. I'm just doing the sort of very simplest ones.
Are there any things I could put in the 6-dimensional theory which will be forbidden to, and not to say, which will not correspond to anything in the 5-dimensional?
No, that's the glory of it. So the point is that the anything you compute in the 6-dimensional theory, you're supposed to be able to compute also in the 5-dimensional language. But let me say exactly what that means. So.
Okay, let's just say your surface has to be flighted over the circle coordinate, right?
Oh, absolutely. I would just take. I mean, in fact, so far I was literally taking. In order to get this simple thing for the surface defect. Yeah. So let me just say I'm saying just the simplest possible thing. So imagine that the surface is literally just literally the circle cross some loop in the transverse 5. Then it's literally this, and otherwise it would be some more complicated story. I'm just trying to give you a feeling for what it means to say that one theory reduces to another one in the low energy limit. So the low energy limit part is the part that we haven't yet really absorbed. You notice this can't be completely precise because, for example, I completely lost the information about where these things are in the 6th direction, right? And that makes a big difference up here. The correlation function really depends on where these things are in the 6th direction, how close together they are. So obviously I'm losing some information here, but let me try to say precisely in what sense I'm losing information. Yeah?
Because the TIF, little t phi f,
Yeah.
upstairs thing, I thought the value of that assembly was supposed to be a number. Whereas a big phi in the downstairs theory,
Yeah.
you said that big phi is an element of add p.
Yeah, it's adjoint value, but then we're applying to it this invariant polynomial. Right.
So if instead of labeling the PI upstairs by numbers, if you label that by covectors of R5,
Yeah.
is there a way to describe the thing downstairs in the same way?
It would have been just the same here. I just would have. I mean, here I labeled this by 5 numbers, but I could have equally well said.
So did you have 5 different sections of that bundle? How do you combine it into one?
No, it's one which is valued in the bundle tensor with R5.
Okay.
Yeah, I shouldn't have introduced the spaces. Okay, so there's some mapping between the different kinds of observable here.
I have a question.
Yes.
So I know you're supposed to get 5D gang mills.
Yes.
Plus extra stuff.
Yes.
Right, and that extra stuff doesn't contribute more I mean, you're saying you forget about that when you're translating from the. You can get everything just from this Lagrangian and all the.
Well,
from that theory.
now what I'm not saying, I didn't so far write a formula, right? I didn't so far say that the correlation function here equals the correlation function here, and that's certainly not true. It couldn't be true. So there's going to be some loss of information in going from this to this. This is not supposed to capture the whole physics of that six-dimensional theory. I just spent a long time telling you how the six-dimensional theory is really hard. So it can't be that I'll get it by just this simple thing. But nevertheless, what I want to say is the following. So we want to say what's now a slightly well, okay, so when we say that this theory X, G, on the circle reduces to 5-dimensional super Yang-Mills at energies much less than 1 over R. So I need some kind of operational meaning of that. So I think one way of saying what it means. So let's compare correlation functions here and here. And let me give these operators a more congenial name. Let me call these operators OUV. So these are in Tudor's terminology, the ultraviolet, the high energy physics. Call that the UV. And let's call these operators OIR. So I'm just suppressing all the labels now. I just want to compare the UV and the IR quantities. So it means, for example, that if we compute, so let's take a OUV of xi and x6i. Let's take a correlation function, so a product over I of these things. And let's now, to understand what low energies means, that has something to do with the wavelength. It doesn't have to do with position space. So let's take the Fourier transform of this. So let's take the Fourier transform of this and compare it to the Fourier transform in the 5 x directions. And we compare it to the Fourier transform of the infrared thing. So we're not saying they're equal. That's impossible. But what we're saying is that their low Fourier modes agree. So if you just study observables, which are, so to speak, the kind of long wavelength observables, and what I mean a little more precisely is that that these will agree up to corrections which are of order the scale of the momentum that you study. So we have this Fourier variable k divided by times r. So in other words, it's very accurate. So this is a very good approximation if the momentum is much less than 1 over r. That's what I said before. So this, in some sense, works at scales which are much less than 1 over r. But what it means is, so for example, it means this kind of statement. Okay, so this is this notion of having a low energy or an effective field theory description of a situation. You have some very complicated field theory, and you can't understand it completely, but you can understand completely some part of it. You can understand what it behaves like. And literally, physically, the way you should think of this really is that if you were an experimenter probing this system, being able to study only the low Fourier modes is like saying you only have a finite amount of energy that you can put into your accelerator. So if you study this thing, for example, by actually scattering particles, this literally says, these Fourier transforms are exactly what you would need to compute if you wanted to study scattering experiments whose typical energy scale was this scale here. OK, so there's some kind of map, and this we're going to see over and over. It's also going to be used, I think, a lot in tutors' talks. This idea that you can have two field theories, and there's a relation between the field theories, this low energy limit, which is a map of everything in the theory. So every observable in the theory is supposed to have some corresponding thing in the infrared. So there's like a flow. There's a flow which takes you from the ultraviolet observables to the infrared observables. So you literally have this thing, and you ask, what does it look like at long? What does it look like at long distances? So that'll also be the sort of key thing in this construction of the new coordinates on the Hitchin space. Well, OK, so let me at least indicate for next time where the Hitchin space is going to come into this story. So sorry, before I do that, I want to emphasize one more point about this. We should not think of, we shouldn't think of passing to the low energy limit as like some kind of poor man's substitute for the real thing. You don't want to think, oh, this is some approximation which only captures a little bit of the information. It's not as good. It's more like the following. Let me give you an analogy. Suppose that you want to study water. Suppose that you want to study a bowl of water. What could you do? One thing that you could do is you could write down the fundamental theory that describes that water. And that means using QCD, right? You would have this, the whole standard model. You would describe every single one of those, of the particles there, 10 to the 23, whatever particles in that thing. And you would solve the equations on some enormous supercomputer, and you would find the answer to whatever question you cared about. And then if you had another question, you would have to do it all again. And if you had another question, you would have to do it all again. That's not a good way to do the thing. That's what it means to use always the UV description. What you want to do, it's not easy, right? What you want to do is somehow figure out what are the equations that govern the thing at the scale you actually care about. If you actually care about water waves, you don't care about shooting the thing with a laser, right? What you care about is just the propagation of water waves. What you need is the infrared description. You need this low energy description where you've thrown away all the irrelevant stuff. And what you have left is an effective Lagrangian that describes the actual degrees of freedom you care about, which is the water waves. So what you want is, in that case, whatever it is, the Navier-Stokes equation, rather than QCD. So this is not just some sort of, this often leads to an enormous simplification of the thing. So for example, I guess I'll say a little bit more about it next time, but the whole thing about Seiberg-Witten theory, the whole power of Seiberg-Witten theory versus Donaldson theory is exactly this. It's passing to the infrared description of the physics. So Donaldson theory is complicated, it involves SU2. Its infrared description involves U1 and is much, much simpler. So this is really a powerful thing in quantum field theory. If you can somehow find the infrared description, it's a much, much better thing to have in many situations. So that's the tool that we're going to use next time. Yeah, so I guess I'll stop there. So I'm sorry I didn't get to the Hitchin system, but I'll get to the Hitchin system.